Hello, I am Bao Quan from Nanyang Technological University, Singapore. I am glad to introduce our recent work on 3D point cloud attribute compression. Here is the outline of my presentation. I am going to introduce it from the following 5 aspects. A point cloud is a set of points used to represent a 3D object or scene. Each point is associated with geometry and possible attribute information. As an efficient and flexible 3D representation medium, point cloud is being widely used in various domains such as virtual reality, image-based localization, autonomous driving. Unlike a polygonal mesh, it represents a model merely with a considerable number of points. This will be at the expense of increased storage overhead, especially when it is used to represent a high-resolution model. Such a large volume of data poses great challenges for efficient data storage, transmission, and processing. Point cloud compression therefore becomes a necessity for many applications. To alleviate this situation, a large body of work has been carried out to develop both effective and efficient point cloud geometry and attribute compression schemes. Existing methodologies can be broadly classified into 2 categories: tailored codecs for point cloud data, and image or video-based codecs. For the first category, existing solutions are mainly based on actree decomposition of 3D space. Among them, G-PCC is one of most representative codecs. However, it is more suitable for sparse and noisy point clouds. Deep neural network-based coding has also emerged as a promising technique that is gaining increasing attention, but previous work mainly focuses on geometry compression. For the second category, existing techniques are to transform the attribute of a point cloud into a synthetic image, and leverage existing sophisticated image or video codecs to eliminate the information redundancy. However, there are still many limitations in the process of patch segmentation and attribute image generation, which makes it less effective in exploiting the spatial correlation among points. The pipeline of the proposed framework mainly consists of 3 steps: point cloud preprocessing, geometric structure analysis and patch segmentation, and attribute image generation. Initially, a given point cloud is simplified into a relatively sparse one to speed up subsequent processing. In the second step, we segment the point cloud into fine-grained patches that are suitable for dimensionality reduction. And finally, an attribute image of the whole point cloud is synthesized after performing embedding, rasterization, and packing. Sophisticated image or video codecs can then be employed to compress the attribute image. To decrease the computational complexity and address the region overlapping issue in global parameterization, we introduce a heat kernel signature-based method to segment a given point cloud into meaningful parts. The HKS is a feature descriptor based on the concept of heat diffusion over a surface, and is used to describe how the heat of each point changes as a function of time. We quantize points with similar HKS function values into clusters, and then perform adjacency analysis on the clusters to segment the point cloud into meaningful parts. To harvest a collection of patches that can be embedded into 2D domain, while maintaining the spatial correlation among points as much as possible, we introduce a complex point-based segmentation method to refine the detected chains into fine-grained patches for nonlinear dimensionality reduction. For each point in the simplified point cloud, we find its k-nearest neighbor and embedding the points into 2D space using multidimensional scaling. This figure shows 3 examples of the visualization of point complexity distribution, where high complex points are rendered with red color, while low complex points are marked with blue. To detect complex points, we identify a collection of candidates by finding points with local maximum complexity from high complex regions. Toward this end, we develop a point cloud complex point detection algorithm, based on a robust and efficient hierarchical clustering method used in mesh parameterization. Each obtained patch, we carry out dimensionality reduction to transform points from 3D to 2D, while preserving geodesic distances between points. We then rasterize the transform 2D patches to synthesize a series of attribute images by formulating the attribute image generation as an assignment problem. To generate an attribute image of a whole point cloud, we assemble all the obtained attribute images of patches into a new image canvas by formulating it as a 2D bin packing problem. Here, we adopt RectPack, a fast and effective nesting tool, to perform the patch image packing task. To evaluate the effectiveness of the proposed method, we conducted extensive experiments by comparing it with peer methods on a public point cloud dataset. The point clouds used in this paper are 10 models that have been widely used as a standard dataset for the evaluation of point cloud codecs. The top 5 point clouds are well constructed, uniform and dense, while the bottom 5 point clouds are relatively sparse, noisy and with non-uniform point distribution. We leverage 3 well-developed image codecs, JPEG, WebP, and MPEG, to compress the obtained attribute images of point clouds. To verify the efficiency of the proposed method, we conduct an experiment on the dataset with RAHT as a baseline method and compare it with 2 state-of-the-art point cloud attribute compression codecs, including GSR and MPEG G-PCC. The image codec we adopted for this comparison is V-PCC. Overall, compared to the baseline method, the proposed method outperforms peer codecs and achieves a bitrate gain by 41.79% on average. We can also see from the figure that GSR and G-PCC reduce the bitrate by 38.24% and 13%, respectively, and this demonstrates the feasibility and effectiveness of the proposed scheme. We also re-implemented the functionalities of V-PCC and conduct an experiment to examine the coding gain brought by the fine-grained patch segmentation. The experiment results show that the proposed scheme achieves a bitrate gain by 32.98%, on average, on the 4 dense and uniform point clouds. We carry out another experiment to evaluate the effectiveness of the different attribute image synthesis schemes, that is, the original canvas, and rectifying the initial canvas into more regular blocks. As can be seen from table, the patch rasterization and rectification scheme introduced in this paper is superior to the scheme O under all the 3 codec settings. Since the block size for rectification could have an impact on coding efficiency, we compare the compression performance under 3 block size parameter settings. We can see from the table, the performance of the rectification scheme with a block of 16 is better than that with 8 or 32, and is thus adopted in our method. In addition, we compare the proposed method with the MPEG V-PCC to investigate the time complexity of different point cloud compression methods. The encoding complexity of the proposed method is generally higher than that of the MPEG V-PCC. This is because the proposed method consists of several more sophisticated geometry analysis and processing components, like nonlinear dimensionality reduction. In summary, we have presented a new attribute image synthesis method for point cloud compression. The core idea is to segment a given point cloud into fine-grained patches that are suitable for attribute image generation after performing dimensionality transformation, and achieve better point cloud attribute coding than peer methods by leveraging existing well-established image and video codecs. For future work, we will explore more effective and efficient image generation schemes to improve point cloud attribute coding performance. Besides, we also plan to develop new methods for point cloud parameterization, which could be a promising solution to maintain the spatial correlation among points during dimensionality transformation, and thus achieve better point cloud compression efficiency. Thank you for your time.